you'd be best able to solve it by graphing. So let's back up just a little bit. Alright, so I have A, B, C, D, and P, Q, R, S. A starts at negative 8, 8. So negative 8, 8, about there. B is at negative 4, 8. So here. C is at negative 4, 4. And D is at negative 8, 4. So essentially I have a square. Okay. And the distance between these points is, I go from negative 8 and negative 4, so there's a distance of 4 there. And 8 and 4, there's a distance of 4 here, and 4 here. So those are each 4 long. So far okay? Then I'll do PQRS, and I get negative 10, 10. Negative 2, 10. Negative 2, 2. And negative 10, 2. And I have another square. And if I look at the distance between negative 10 and negative 2, that's 8. This one's also going to be 8, and these are all going to be 8. So I have two squares, one inside the other. One has lengths of 4 and one has lengths of 8. So then when I look at my answer choices, I've got similar, I've got have unequal sides. Well, that's not true. They're not congruent because one's 4 and one's 8. Congruent would mean they were the exact same size. We have that they're similar. Because they're both squares, and because there's a proportion between them, PQRS is 2 times the size of ABCD, so that's similar. So we've got the 8. Does that make sense? So basically with similar figures, you're the exact same shape and the exact same proportions. It's just like somebody put you in the copy machine and enlarged you or reduced you. Does that make sense? Okay. Okay. Do you guys remember concave and convex in term 1 for those that were here? Yeah. Convex, all of the vertices are going to point out and you've got kind of like a nice shape. And concave is when one of the sides is caved in. And that's like how you can remember concave caves in. So this obviously is not like a nice sort of shape, right? It's got that side that's all crushed in. So it's concave. So we can get rid of the 2 convexes. And we just have to count the sides. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Nonagon is 9. Hendecagon is 11. You may not remember hendecagon being 11, but you should remember non for 9 because they sound similar. And you only have the 2 choices, so you'd be able to rule it out to get to the hendecagon. So we've got a figure here, and she's saying it's convex and irregular and octagonal. Okay, it is irregular, and we can count the sides and see if it's an octagon, but is it convex? No, because this little corner caves in, right? So it's not convex, it's concave. Not too bad, I hope. Okay, now this one, to be honest with you, is very kind of complicated, not because of what you'd have to do to find the exterior angle, but because of the way they described the process in the answer choices. Okay, so we have a regular decagon with isosceles triangles. Okay, that means that each of these lengths is the same because they're isosceles. Okay. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. It's a decagon, so that's 10-sided. So 10 triangles. Now, each triangle is 180. This top part right up here, all of these are going to add up to 360 because you see how it makes a circle? Well, I'm going to divide by 10. Yeah, because each of these will be 36. Because I'm going to do 360 divided by 10 to get the 36 because each of these corners or these vertices of these triangles will make a circle if I were to draw around here. Can I see that? And a circle is 360. So each of these would be 36. Actually, it let me reread these. Okay, we have add all the angles of in the triangle together to get 180. That's not going to help us find an exterior angle at all. Okay, add the base angles of the isosceles triangle together to determine the measure of the exterior angle. The exterior angle comes out like this. Okay, and what we have is this line here will add up to 180, correct? And this is an isosceles triangle, so that means each of these base angles is congruent to each other all the way around. So yes, we would subtract the base angles because these two base angles are subtracted. We'll find that 180. So, but we're not going to subtract them from the interior angle. We're going to add the base angles together to determine the measure of the exterior angle. We're going to add these two base angles together first. We'd have to subtract them from 180. See what I mean by the wording on this is not great? So you have to read all of these carefully. So find the measure of the non-base angle that is congruent to the exterior angle is another choice too. So you kind of are doing all of these things. This is actually the most accurate one because these two and that together add up to 180, correct? These two are the same as these two, and this one add up to 180, so that means that this angle here and this angle here will be the same. It's the way they worded it is very complicated. And each of these three sound like it could be right. And so you kind of have to like work through it as if you were going to try to actually find the measure and see which one works. So if I did all this and I actually did the math and I came through and I came over here and I'd say, okay, that's 36, so I'd do 180 minus 36 would give me 144, and I would divide that by 2, so each of these would be 72. And then I would take these two 72s and subtract from 180 and find out that this is 36, and then I would find out that these match. Does that make sense? So that's how I would kind of work through to find out which of these answers is the correct one, by actually completing the problem myself. Just because the wording is awkward. To find the total angle measure of a polygon, we have to do that 180 times n minus 2, where n is the number of sides. Right, so we would do 180 times 10 minus 2, which is equal to 180 times 8, which is equal to 1448. No, 1440, sorry. 8 times 0 is not 8. And then you would divide that by 10, and you get each one of these is 144. Like each one of these whole corners is 144. So this is that formula. So the whole decagon is 1440. It's the circle inside that's made up of the triangles that is 360. Does that help?
I think so.
Okay. All right, let's look at this guy over here. He's a barn. These match, these don't. And since it's hard to see, that's 134 and that's 128. Okay. So I have 1, 2, 3, 4, 5, 6 sides. So I'm going to find the total angle measure of this figure, and it's a 6-sided figure, so I'm going to use that formula we just talked about. And it's got 6 sides, so that's 180 times 4, which is 720 degrees. 6 minus 2. Yeah, it's always the number of sides minus 2, and then times 180. Okay. So the whole thing is 720. So that means each of these is going to add up to 720 when you add them all together. Well, I have 2 of the 5x plus 8s. And I have 2 of the 10x minus 4s. And I have a 134 and a 128. And I ran out of room, but those will equal 720. So far, okay?
And then
I'm going to just distribute the 2 here and here. So 10x plus 16, 20x minus 8, and that equals 720. Then I want to add together my x's. So 10 and 20 is 30. And I want to add together all my numbers. Okay, so I've added the numbers together, 270, so that equals 720. I'm going to subtract that 270 from both sides. $30x is equal to 450. Divide by 30, and x is going to be 15. Okay. The question though was not what is x. Be really careful with that. The question is what is the measure of angle F? And angle F is right here, 10x minus 4. So we're going to plug the 15 in. And we get 146 degrees. Okay. Which would go right here. Any questions about that one? So it's a 3-part problem. First you have to find the total angle degree of the figure. Then you have to solve for x. And then you have to plug x in. And find the angle that you were looking for. Go over it. A translation, there's a couple different kinds of translations, so I want to go over those really quickly. Okay, you have a dilation, And a dilation will either stretch or shrink. So that problem we just did with the square where one was bigger than the other, that would be a dilation. Like if you took a small square, you dilate it by times 2, or if you took the big square, you shrunk it by times 2, right? So that's a dilation. You have a rotation, which like turns the figure. So for example, if I had a triangle like this, I could rotate it and it would go like that. So you can rotate by like 90 degrees, 180 degrees, 270 degrees. If you rotate 360 degrees, you're back where you started. This would be a 90 degree to the right. That would be because I rotated it. Okay. Then you have what's actually called a translation, which is where you move it. So if I have a circle here, I could move it over here. And that, like I would move it like, say 2 up and 1 back or something like, or 2 back. You move it up and left and right and up and down. And then finally you have what's called a reflection. And that's kind of what it sounds like. You're going to flip it. So if I'm here, I could have a triangle like that. Let me back up a bit. Flip over an axis, and I could reflect it over the x-axis. And so it's like a reflection. You're going to look exactly. You know how when you look in the mirror, you're backwards, or you know if you try to read in a mirror, it's backwards. It's like that. So when you flip over, like this line would be the mirror. And so you have the reflection. Or you could flip it over this axis and it would look the same because the triangle would be the same on both sides, an isosceles. But if it was a different kind of shape, it might look different if you reflected it over the y-axis. So basically you just take it and you flip it over the axis like that. Okay, so those are the different kinds we have. Any questions about what those do? Then for this one, we have some movement that's going to occur. So what I'm going to do is I'm going to draw LMPQR in purple. And then I will draw, see how these have L1, M1, P1, Q1? That's letting you know it's the same shape, it just moved somehow. So I will draw that one in red. And then we'll compare the two figures to decide if it rotated or shrank or moved or whatever happened to it. Okay, so I have 4, -2, 5, +2, 8, 5, 6, 7, 8, -5, 6, -7, yep, oh, sorry, and 2, -4. Okay, so I'm going to go, right, L was here, L, M, P, Q, R. So we've got some sort of a thing. It's a pentagon. No, yeah, it's a pentagon, but it's a weird one. So now the new one is at -5, 1, -5, -1, -4, -1, -1, -4, -3, -6, and then -7, -3. That's not the same shape. Hmm. 1, 2, 3, 4. 1, 2. Oh, 5, -2. That's what's wrong. I read that wrong. Sorry, it should be like this. So it is the same shape.
It's 9 to the left of 1.
Hmm?
Is it A?
Well, we didn't move up at all, right? Or, sorry, we did move up 1. We're here at -2, and we're here at -1. So yeah, we moved up 1, and we moved left, right? So we went from here to here, so that's left, and then we went up 1. So left 9, up 1. Okay. If it had flipped, it would have looked exactly like this, only the opposite, like the opposite way. Does that make sense? Any questions on that? Basically, if we had rotated it and it flipped, all the x's would be exactly the same except negative instead of positive. And then the y's would be the same.
Could you just not have subtracted one from the other and figured that out, like L? Took L, subtracted it, and
You would want to do that to all the points?
So, what was the primary rate?
Yeah,
How can you explain that again? I'm sorry.
y's. So, okay, remember clockwise goes this way, and counterclockwise goes that way. So if we're going 185 degrees counterclockwise, okay, this is 90 degrees. So that means each dot is how many? From O to N would be 90, so from O to N is going to be 45. So they're 45 degrees each. So if I take 185 and I divide it by 45, I get 4.1. So I need to move a little more than 4 dots. So I'm right here, so I go 1, 2, 3, 4, and I'll end up somewhere in this general area. So between R and Q. So to do something like this, you want to figure out how much space, degrees-wise, is in between the dots.
And you would just subtract it from 360?
Subtract what from 360?
185? You look at it as a clock, and you put, your first degree,
So this would be like 0,
yeah, and then 360 would be,
back to here. I suppose that would work. You could also look at it as 185 is just a little bit beyond a straight line.
that's what I'm saying, if I flipped it as 360, I knew 180 was exactly across from where
Yeah, there's more than one way to do this. Absolutely. Big thing? Gotta remember those. Because if you went the other way, it'd be between S and R. So remember clockwise and counterclockwise. Okay, we have similar rectangles, which means they're going to be in proportion, correct? Oops. Okay, maybe I zoomed in too much. Okay, so we have rectangle A, length is 13, oops, this is number 31, and rectangle B, length is 6.5. And what's the relationship between 13 and 6.5? Yeah. So we want to find what could be the length and the width. Well, first of all, rectangle A, Oh, length of the diagonal. Sorry, I didn't read this. So here's rectangle A. This part's 13. Here's rectangle B. This part's 6.5. We can eliminate D right away. The diagonal is going to be longer than either side. So you can't have a side longer than your diagonal. So we can eliminate D. And we can look at the diagonal on B is 6.5. And so this one, 7, is too big. So we can eliminate B. So now we only have to consider A and C. Does that make sense? So now we're down to a 50-50 chance. Okay. Which part?
Just the whole column.
Okay. We've got the drawing, okay?
Yeah, I understand that part.
Okay. When you have, this is a right triangle,
Mm-hmm.
because these are going to be right angles. And if you have a right triangle, this length and this length are going to have to be shorter than that length. The hypotenuse is always the longest side. So when I realized I had the right triangle, I immediately knew that both of these were going to have to be shorter than that. And the same thing over here, if I call this like X and Y, these are going to have to be shorter than that. So when I went in, I start looking at their, okay, those are shorter, those are shorter, those are shorter, but that's longer. So I can get rid of that 14, because it can't be, 14 won't work. Does that make sense so far?
Yeah.
That's all the A's, and the A's allowed me to eliminate D. Then I started looking at the B's, and this one had a 7, and 7 is bigger than 6.5, so I was able to eliminate B. So now I'm down to just A and C. And the reason you want to eliminate some of these is because to find out the possibles, you want to do the Pythagorean theorem.
Could it be an
That's it. And the Pythagorean theorem is a squared plus b squared equals c squared. So I'm going to just try these. 5 squared plus 12 squared, well, that equals 13 squared. This is 25 and 144, and that does equal 169. So that one will work. And then I want to try the same thing for b and do 2.5 squared plus 6 squared. Does that equal 6.5 squared? And yes, they do. I get 42.5, or sorry, 2.25 and 42.25. So it's A. Oh, sorry. But by eliminating them, if it hadn't have been A, then I would have had to try B, and then I would have had to try C. Well, by eliminating B, I can skip it and just go straight from A. And since I've eliminated both B and D, if A didn't work, it had to be C. So then I only had to try one. And once I tried that one, I knew the answer. Does that make sense? So whenever you can eliminate things that are impossible, like this leg being too long, you greatly reduce the amount of work you might have to do.
How do you know which
Right here, this 14 is bigger than 13, and 13 is the hypotenuse of the triangle, so that has to be the largest side. So I knew I could eliminate that, and then I could eliminate B because this 7 right there is bigger than the 6.5. Brennan is making a poster for Drama Club. And it's a regular pentagon with side lengths of 12 inches. And the school wants to put up a giant replica of the poster during the athletic events. And we want to make the length 8 times the original. So how many times larger is the area? All right, well, we don't have to necessarily do this problem completely. I could do a 1 inch pentagon. So I could do 1 inch square. And I could do an 8 inch square. And this area is 1 and this area is 64. How many times is the area? The side lengths are 8 times the original, correct? And the area is 64 times the size of the original. You don't actually have to find the areas. You square the number of times the length.
So you just square 20?
You square 8. They want it 8 times the original, so you square the 8. So if you were to make a poster 10 times the original, you would square 10, and so the area would be 100 times the original. Does that make sense? So let's say I'm making a poster that's a rectangle, and it's 10 inches by 13 inches. And then I want to enlarge it by 5 times. Then the area of the big poster would be 25 times the area of the small poster.
I just read it wrong. You just want that.
You just want
How
the,
much bigger?
how much bigger? Yeah, just how many times larger is the area. So to find out how many times larger an area is, you don't actually have to work out the problem and find the area of the first one and then find the area of the bigger one and then subtract them. It's a lot of work, right? If you know how many times bigger, you just square that. Make sense? Okay. No. So far, we haven't hit another final problem. Okay. We've got a toddler section of a park is in the shape of a trapezoid. Here's the park. We've got 8 meters here. The section was remodeled to have an area that was 96 square units more than the original area. Okay, now in this one we are going to need to find that. Oops, can't read it, sorry. Okay, so first let's find the area of a trapezoid. And the area of a trapezoid is equal to base 1 plus base 2 divided by 2 times height. So, I'll just do it on here. 10 plus 14 divided by 2 times 8 is the height or the area of this trapezoid. So 24 divided by 2 times 8. So 12 times 8, which is 96. Okay. When they remodeled it, they added 96 square units, so they doubled the area. To 192. Now, how could we double this?
Just not divided by
Okay. Well, you have to use the same formula because it's still a trapezoid, right? They kept it a trapezoid, they just doubled the area. So if we look at this, the height was doubled. If we made this 16, we get 12 times 16, which would give me 192. So that works. Doubling the height does double the area. If that hadn't worked, then I would say, okay, well, if we multiply the height by 4, what happens? If we double the length of the sides, the parallel sides, what happens? You know, you just see what happens when you do these different things. But first, you need to find the 2 areas so that you can make those comparisons. Does that make sense? I don't know. All right, we have a right triangular flag of a sports club. Was designed to have a base of 4 feet and a height of 6 feet. So we have a right triangle flag, and it has a base of 4 and a height of 6. Okay, so I drew that backwards, but whatever. The sports event, the club made a new flag by doubling the base and height of the flag. Okay, well, if they doubled these, they increased it by a factor of 2, correct? So to find out how much larger the area is, I'm going to do that and square it. So the same as we did in this problem. So you find that doubling the length here and here doubles the overall size of the flag. So we square the 2 to get the new area as 4 times the height, or 4 times one.
Wait, how come you square stuff just multiplying by
You wouldn't, because you're multiplying the sides by 2, that the length is side times side. So you're getting a times 2 and a times 2, and then your area is side times side, so it's 2 times 2. Area is like squares, right? So if you have one square, these are all 1, and the area is 1. If I double it and I have 2 times 2, the area is 4. If I double it again and I have 4 times 4, the area is 16. So every time you double the area, you're making the squares bigger that the area is made up of. Does that make sense? So doubling the size of the squares, actually, you square it to get the new area. So if I made it 3 times as large, I would get a 3 times 3, which would be 9 times the area. Does that make sense?
So then, what's the answer?
Your answer is 4 times more. That's what area is. All area is are like tiny little squares. So if you're talking square inches, you're literally a bunch of little 1-inch squares. How many fill up the space? If you're talking square feet, it's how many 1 foot squares, like the tiles that are 1 foot. How many tiles fill up the space? So if you double the size of the square, the area ends up being 4, because where there was 1 square, this is a 1 and 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 a 1. You get 4 in there. Does that make sense? So that's why you take however many times the length, but then you square that, because that's how many squares you added. Does that help?
Yeah.
Okay. Okay. This is possible kind of a final question. We have 2 triangular flower beds, and my markers. We've got one side that's the same, okay, and then an angle that's the same, and another angle that's the same, and I have side, angle, angle, side, angle, angle. They go in the same order. Well, side, angle, angle is the same as angle, angle, side, which is a congruent. So these 2 triangles are the same. So they have the same perimeter. Oops, I circled the wrong thing. Don't, that one. They have the same perimeter. They'd have the same perimeter, the same area. BC and PR would be the same length. AC and PQ would be the same length. So anything that was talking about which parts of them were the same. Does that make sense? Another refresher. For triangle congruence, we have side, 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 angle, side, angle, side, angle, and angle, angle, side, but not angle, side, side. Oops. Okay, so it can be any of these 4.
How do you get 30, 36?
Hmm? Oh, we're going to do that one next, and I think we'll stop there for today because it's a lot to digest.
And a side angle.
You can do, well, angle, angle, side, and side, angle, angle are the same thing, so it really doesn't matter which order they go in. We just put AAS because it's alphabetical.
Yeah.
But it's the same thing, it doesn't matter. So like if on a test that I was giving you, you wrote side, angle, angle, I would not be like, nope, that was supposed to be angle, angle, side, you're wrong. No, that would be silly, right? Be mean. You're not mean.
Are you supposed to start off with like a specific letter?
No, typically you would go alphabetical, I guess, but in this case that doesn't really help you. So you just look at what parts are the same and go in the same order around each triangle and see if everything matches up. But you can go, I could start at P and C and go this way, or I could start here and go that way. It doesn't matter which. Okay, 36 is where we're going to stop today. I have angle A is congruent to angle BDE. So this angle is congruent to this angle. Okay. The area of triangle ABC, so the large area, is 240 centimeters. The area of angle BDE is how many? Well, okay, because these are two different size triangles, they have the same angle and these two are in proportion by a factor of 2. Okay, so ABC is 2 times the length of BDE or whatever. Okay, the triangles twice, which means the area is 4 times as large because I did the 2 squared to get the 4 times as large. So to find the area of the smaller triangle, I have the area of the large triangle, I'm going to divide it by 4. Okay, so BDE would be 60 centimeters squared. Did that make sense?
Why'd you get 4 times larger?
Because
Really
the
twice?
length is twice as long,
Yeah.
and then for the area, you square,
Oh, okay.
so that gave me the 4.
Okay.
And so then I divided by 4 to get the 60. Now, if I had the area of the small triangle, I would multiply by 4 to get the area of the big one. Does that make sense?
Mhm.
All right, so we'll stop here.